Okay, working with infinity times 0. So in here we can see this is going to be infinity, and as this denominator gets larger and larger, the whole fraction gets to be 0, and the sign of 0 is 0. So both of these are going to be an infinity times 0 situation. So how do we handle this? Well, the limit as x approaches infinity of x sine of 1 over x, we can rewrite this way. So this is the same as this. Now, what's that advantage? The advantage is now this is going to be 0, and this is going to be 0. So now we can just approach it the way we do L'Hopital's rule and take the derivative of the numerator and the derivative of the denominator. So this is going to be cosine of 1 over x, and then you've got to use the chain rule times negative 1 over x squared, and this will be negative 1 over x squared, and these will reduce, and I'm just going to have to substitute in, taking a look at as the denominator gets larger and larger, this becomes cosine of 0, and cosine of 0 is 1. And you can see that as we approach infinity, the y values are getting closer and closer to 1. And the argument is the same for the b. We can go through the same kind of thing. Okay, working with this indeterminate form, which is infinity minus infinity. So as x gets closer and closer to 1, this denominator here gets close to 0, which makes the whole fraction get large. As x gets closer and closer to 1, makes this denominator get close to 0, which makes the whole fraction get close to infinity. Okay, so again, we want to do the same strategies we've done before. We want to somehow get it into a quotient look. And to do that, I'm going to multiply numerator and denominator by x minus 1 so I can get a common denominator. And I'm going to multiply the numerator and denominator by the natural log of x. And so I'm going to have x minus 1 minus the natural log of x, and the common denominator is x minus 1 times the natural log of x. Now, the denominator will be, as x gets close to 1, this is 0. X gets close to 1, that's going to be 0, so 0. And then again, we're going to have 1 here, that's 0, and getting close to 1 here, that's 0. So we have changed this form into something that's a little bit more comfortable. All right, now we're going to take the derivative of the numerator and denominator. Now that's going to be a 1 minus 1 over x. And in here I have to use the product rule, so that'll be x minus 1 times 1 over x plus 1 times the natural log of x. So now I'm going to have the limit as x approaches 1 of 1 minus 1 over x, and if I distribute, I'm going to have 1 minus 1 over x plus the natural log of x. Okay, as x gets close to 1, this is going to go to 1, and this is going to go to 1, and we're going to have 1 minus 1, which is 0, and down here we're going to have natural log of 1, which is 0 here. So this is going to be a 0 over 0 situation. Let's go ahead and undo this. So I have a 0 over 0 situation again, which is going to allow me to use L'Hopital's rule. And this will be 1 over x squared all over 1 over x squared plus 1 over x. And allowing this to be equal to 1, I'm going to get a 1 in my numerator, and down here I'm going to get a 2. So the limit is going to be equal to 1/2. All right. Now there are other indeterminate forms that don't take on the other looks that we've seen before. They take on this kind of a look. And when they take this kind of a look, what we're going to do, the strategy that we're going to use is we're going to work with taking the limit of the logarithm of the function and seeing how that's described. We'll go back to this definition after I've done a problem. Okay, so we have this situation where this is, in the denominator we have a 1 as x goes to infinity, and then this is going to be infinity. So this is the indeterminate form we're working with. All right, so what we're going to do is this. We're going to find the limit as x approaches infinity, and what we're going to do is we're going to change the look of this, and we're going to write e to the natural log, and then we're going to do it of 1 plus 1 over x to the x power. So remember, these two are inverse functions, so I haven't really done anything to the problem other than to make it look more complicated. So this is e to the natural log of this. So I'm going to concentrate my efforts on finding the limit of this expression right here. I want to find the limit as x approaches infinity of this exponent, natural log of 1 plus 1 over x to the x power. Now, one of the properties of the natural log is I can bring this exponent as a coefficient. Now, this situation is going to be infinity, and then this is going to be a 0, and then times 0. So that's one of our indeterminate forms that we've looked at before. Remember, the strategy is to try to make it look like a quotient. And I can do that by saying the natural log of 1 plus 1 over x all over 1 over x. And this is going to be a 0 over 0 situation. So now I know I can use L'Hopital's rule. This will be the limit as x approaches infinity. And the numerator is going to be 1 over 1 plus 1 over x times using the chain rule, and that'll be negative 1 over x squared. And this is negative 1 over x squared. And I can do some reducing here. Allow x to go to infinity, and that answer is going to be equal to 1. Now, all we've done here is we found this limit right here. We have found the limit of that. So now I know that this will be equal to e. E is a constant here, and now I have found the limit of the exponent, and the exponent is 1. And so this is equal to e. And I don't know if you remember from prior experience last year, we did look at this limit, and we did look at it as e. I think all we did was look at it graphically. We just graphed it and noticed that it was getting closer and closer to that particular number. Okay, let's take a look at another indeterminate form, and this one is a 0 to 0. Anytime you have these exponent expressions, you want to use the strategy I just used a few minutes ago. So we're going to take the limit as x approaches 0 from the right-hand side. Oh, by the way, you can only approach from the right-hand side. It really doesn't make sense to look at it from the left-hand side. If you will put that in your calculator sometime and look at it, you'll see that it's not a continuous figure, and therefore we can't take derivatives of it. So this is x to the x, and the strategy is to look at it in terms of a natural log. So I'm going to use another color. I'm going to write this as e to the natural log, and then I'm going to write x to the x power. So my strategy is to look at the limit of the exponent, the limit as x approaches 0 from the right-hand side of natural log of x to the x power. And that is, I can rewrite it as the limit as x approaches 0 from the right-hand side. And again, I can bring this down. And let's examine that. That's going to be 0 times infinity. And we can rewrite that as a quotient. Limit as x approaches 0 from the right-hand side of the natural log of x all over 1 over x. And if I examine that, that'll be infinity over, let's see, that's negative infinity over negative infinity. Let me think, that is positive infinity right there. All right, so we can apply L'Hopital's rule, and that'll be the limit as x approaches 0 from the right-hand side of 1 over x, and this is going to be negative 1 over x squared. We can simplify that, and that's going to be negative x. And that answer we can evaluate, and the answer is going to be 0, which means that this portion right here is getting close to 0. So the answer is e to the 0, and e to the 0 is 1. So this limit does exist, and the answer is 1. Okay, working with the indeterminate form, infinity to the 0 power. So this is infinity to the 0 power. And again, we go through the strategy. We're going to try to find the limits. The limit as x approaches infinity of x to the 1 over x, we can rewrite as the limit as x approaches infinity of e to the natural log of x to the 1 over x. And what we're going to do is we're going to concentrate on finding this limit right here, and that's what they're doing right here. They're trying to find the limit of that. All they've done is bring this exponent down. And it's an infinity over infinity. When you evaluate, it's going to be 0. So this limit right here is going to be 0. So this is going to be equal to e to the 0 power, which is equal to 1, just as we did it in the last screen. And this is the end of the screencast.